Hey there, chemists. In this lesson, we are going to look at reactions that involve aromatic transition states. We actually saw aromatic transition states in the previous lesson when we looked at the Diels-Alder reaction. In fact, that's the first thing you'll see on your notes here. That just means we have a 6-electron transition state. So here is a Diels-Alder, which involves a diene and a dienophile. And the electron pushing would look something like this. 3 curved arrows, 6 electrons. Turns out there's many other reactions we've already seen that have this same feature. Right below it is a cope elimination. This was in our amines unit, and this also involves 3 curved arrows in this one step of the cope elimination, so it also qualifies as what's called an aromatic transition state. There's a few others. I actually want to see if you can identify and fill in the curved arrows for them, just to prove to yourself that this is a common feature. So go ahead and try that now and check back and see how you did. Okay, let's see how we did. So right up there we have a decarboxylation in the top center. I'll just say decarbox. This is from a beta keto carboxylic acid. And remember, this takes an H. You actually generate a CO2 molecule and an enol, which tautomerizes to a carbonyl, but there's the arrow pushing for it. Below that, from last semester, here's an ozonolysis. Also 6 electrons, 1, 2, 3 curved arrows gets you there to get to the malazanide intermediate. And then off in the upper right, this is dihydroxylation, the first step of dihydroxylation. This is when osmium tetroxide reacts with an alkene, and you can draw a transition state with, again, 3 curved arrows. Below it, we have an example of an aldol reaction. This is using what's called a boron enolate. Haven't seen boron enolates yet, but hopefully you can see the enolate architecture right there, just as attached to a boron, instead of being drawn as, let's say, a negative charge like we saw with the enolate anions that we drew a few units ago. The 3 curved arrows would look like this. So this is just to give you a sense that this is a common trend we see in many reactions, and we're going to see it today in 2 more transformations called the cope rearrangement and the Claisen rearrangement. These are both stereoselective reactions, and it's this transition state that we used to explain this. The cope rearrangement was developed by Arthur Cope back in the 1940s, and it involves a diene that is specifically 6 atoms long, and I'll just show you how I like to figure out the products. I number it 1 through 6. You form a bond between 1 and 6. You break the bond between 3 and 4, and the pi bond between 5 and 6 rearranges. So you get a product, if you look at your curved arrows, that looks like this, with a different diene. So we start with a 1,5 diene, and you actually get a different 1,5 diene. And you might say, wow, this is very similar to the starting material. How do we know this reaction even goes in this direction? It is a reversible reaction. However, I've given you an example here that you can hopefully figure out why it's thermodynamically favorable to form the product. We have 2 monosubstituted alkenes, and we're turning this into a disubstituted and a monosubstituted alkene. So if this is thermally driven, you're going to go to the more stable, more substituted alkene in the product. Now, there's also another feature of this reaction, and that it's stereoselective. There is an asymmetric carbon I arbitrarily have here in this starting material, and we actually have stereochemistry in the alkene geometry. I drew the E-alkene, and the result of this alkene geometry is due to the asymmetric carbon that's going in, and I'll show you how we can predict that based on a transition state. So I'm going to redraw the starting material just a little bit differently in a 3-dimensional conformation. There's my diene, and there's the methyl pointing out like so. And hopefully, as you see that I drew this, it is intended to represent a chair. And indeed this is. This is called a chair transition state. And if we imagine what happens after doing a cope, I have the methyl in what looks like an equatorial position if I consider this to be a chair, and indeed it is. This is called a pseudo-equatorial position, because this is a pseudo chair. It's an open chain, but this concerted transition state has this conformation, or we use this conformation to explain the stereochemical outcomes. So I'll just show you how I figure out the products in this case. I'm just going to draw a little dotted line that connects the new bond that I form. And so I'm going to make a new bond there. My curved arrows would look like this. So I'm going to get a new alkene right there. And I can tell I have a hydrogen sticking off of this sp2 carbon, and I have another hydrogen on this carbon here, which is pseudo-axial. And they're more pointing in opposite directions than in the same direction. So the alkene that ends up in between them is going to be a transalkene. Let's draw it and hopefully you'll see what we mean. So our product is going to have a new bond down there. We have a pi bond over here, a new pi bond back there, and the other methyl right where it was. So my hydrogens, which were here and here, are still here, and there they are, more in opposite directions, and you can see I drew a transalkene, and you get the transalkene. So the point of this is that the stereochemistry, the stereochem in the starting material, in the starting mat, translates into the product. There's actually many reactions where this happens, but this is one of the first times that we've looked at this in a little more detail. So let's look at some examples. These are all concerted. There's no real mechanism to show. It's one step, but there are often interesting outcomes based on some pretty interesting examples of cope rearrangement reactions. So let's walk through a couple of them, and again, I'll just sort of show you how I figure out the products. I first find the 6-membered chain that starts and ends with pi bonds, alkenes in this case. I'm going to draw my curved arrows. I form a bond between 1 and 6, 3 and 4 break, and then the bond between 5 and 6 rearranges, and I get a open chain. I'm actually going to draw a transition state first. I'm going to mirror what we did up above and try to replicate that chair transition state a little bit. This one has a methyl, just like the first example. There's a second methyl, and it has to be syn. So if that second methyl is syn, it's pseudo-axial in this open chair transition state. And then when I do the cope, don't worry, you'll be able to cope. I draw a little dotted line that just shows where the new bond forms, and I draw everything the same, but change what's changed. So I have a new pi bond at the beginning and the end of this new chain. I still have my methyl pointing straight up right there, and this other methyl back here. And now in this drawing, I can tell I've got a transalkene on one side, but this is actually a cisalkene on the left. So again, the relative stereochemistry in the starting material has turned into these alkene geometries in the product. We could just open this up and draw this a little bit prettier to really highlight the cis, 1, 2, 3, 4, 5, 6, and transalkene geometries. So let's take a look at a few others. The one right next to it also has a 6-membered chain, 1, 2, 3, 4, 5, 6. I'll first just draw this in a 3-dimensional chair transition state. I'm going to use the same template that we've been using up above. I'll put a little dotted line where they connect. I have that same methyl pointing toward me, so I'll put it in a pseudo-equatorial position in my open chair. This one has these 3 other methyls that are coming off of the alkene carbons. I need to fill those in. So I'm actually going to number my chain so I don't lose track. 1, 2, 3, 4, 5, and 6. Off of carbon 1, I have a methyl, and this is a transalkene in the starting material. So I need to make this alkene trans. That means that this methyl is sort of pointing in what looks like a pseudo-equatorial position. I'm actually going to go ahead and draw the pseudo-axial hydrogen on that same spot. I'm really pretending this is a chair, even though it's open, putting those groups into what look like equatorial and axial positions definitely helps me draw it more correctly in the product. I've still got a few other methyls I have to show. There are these 2 methyls on carbons 5 and 6 out there, and they are cis to one another, so I'll try to do that. That means what looks like I think we'll have a methyl there off of 6 as opposed to a pseudoaxial hydrogen, and then another methyl off of carbon 5. So then if I do the cope, I've already drawn my dotted line. I'm going to draw what is the open chair first. I no longer have that bond back there. New pi bond back there. New pi bond over there between carbons 4 and 5. And then I'm going to just fill in all my methyls where they are. And this will more or less show me what type of olefin geometries I get in the end. So it looks like I have a transalkene here, and then I have a set stereochemical position there. So let me just redraw this. And then I have a methyl down there. Actually, I have 2 methyl positions, don't I? And it looks like one is going up because the H is going down. The other one is going down because the H is going up. There's those H's in my starting material. They're still here in the product, and they are anti to each other. So I need to make sure I show those methyls pointing anti to each other. Okay, so let's try a few more examples, and I'll show you sometimes we don't even get the simple diene that you think you're going to get each time. This next one is an example of an oxycope. I'm going to do the same thing I did before, though. I'm going to start by numbering my 6-membered chain. 1, 2, 3, 4, 5, and 6. I'll draw my curved arrows, a new bond between 1 and 6, 3 and 4 break, 5 and 6 rearrange. And I'm going to avoid the transition state, and you'll see why for a second here, because it turns out this one doesn't have any stereochemistry to worry about. Because if I draw just what I get constitutionally, here's what I end up with. There's no asymmetric carbons. There's a transalkene I arbitrarily drew, but that is not going to stick around like that. Take a look at that functional group. What do you see? I see an enol up at the top, and enols do not stay put. They tautomerize. This is going to tautomerize, and you're going to get an aldehyde. So a cope rearrangement, specifically an oxycope rearrangement, lets us make an alpha, beta, gamma, delta, epsilon unsaturated aldehyde. So if I see that, I can say, oh, I can make that from an oxycope, which is just an allylic alcohol, really just a secondary alcohol. You could make that from a very simple carbonyl and an organometallic or anything like that. Okay, there's another oxycope right next to it, so challenge yourself. See if you could figure out where is the 6-membered chain in this example D, and number it. Figure out just constitutionally what it looks like. This will also undergo a tautomerization. Come back and check and see how you did. Okay, let's number our chain. 1, 2, 3, 4, 5, 6. This is just how I like to do it to figure out what the product is. And it should be noted, I'm kind of arbitrary in terms of which side I'm numbering from. I just want to find the 6-membered chain that starts and ends with an alkene. I'll draw my curved arrows. Actually, no, I'm just going to draw a dotted line to highlight that I form a new bond between carbon 1 and 6. That's what's happened every time. I also break 3 and 4, and the pi bonds rearrange. So I'm going to try to draw everything exactly the same, but only change what's changed. So 5 and 6 is now a single bond. 4 and 5 is now a double bond. This bridge up here is still there. This back half of the bicyclic part is still there. This bond between 3 and 4 is gone. My OH is still there. I now have a new bond, a new pi bond between 2 and 3. 1 and 2 is now a single bond, and then there's a new single bond between 1 and 6. And that's correct. So let me unfold that. And if you look, there's actually 2 6-membered rings attached. Here is one 6-membered ring, and then here is another 6-membered ring. If you can't see that, number them, go count. But you get 2 fused 6-membered rings. So you get what looks like a decalin. and then there's another alkene out here. However, I have an enol once again, and we know that that enol is not going to stay put. You're going to tautomerize that enol, and you will get a ketone. So we also have alpha, beta, gamma, a delta, epsilon, if you're counting all the way from right next to the carbonyl carbon, a delta epsilon unsaturated ketone made from a very fancy oxy-cope rearrangement. Okay, let's try two more and then we'll see a different rearrangement that also has oxygen in it and gives us a different product. This one I'm going to number 1, 2, 3, 4, 5, 6. I form a bond between 1 and 6. 3 and 4 break. 5 and 6 rearrange. I'm going to draw a transition state here because I can tell I'm going to get some asymmetric carbons out of those trans alkenes. I'll use the same template that I have before. And then to make those trans alkenes and then attach these other 4 carbons, I can draw what looks like an open decalin chain. Speaking of a decalin, wow, that's terrible. Let me draw that again. Let's try that again. There's the first one. And then this sort of looks like a chair, if you remember that from last semester. And there are my 2 transalkenes in the beginning. Why did I bother doing this? Well, look at these substituents. Where are they relative to one chair or the other? Everything looks nicely equatorial here. So I could imagine I have pseudoaxial hydrogens on those positions. So let's draw the product of the cope. You form a bond between those 2 carbons. You end up breaking that bond back there. And you will get a new 6-membered ring, which I'll still draw in a chair down there, and then I have 2 vinyl groups attached to that original chair. And I'll fill in the hydrogens, because that helps me figure out what this looks like if I draw this a little bit more cleanly. So what does this look like? I have a 6-membered ring. And then I have 2 vinyl groups that are pointing in opposite directions. And you get that. Okay, one more. Let's number it. 1, 2, 3, 4, 5, and 6. I form a bond between 1 and 6. I break 3 and 4. And then 5 and 6 rearrange. I can tell I'm going to get an enol here. So I'm actually going to just draw it constitutionally without the chair transition state, because I would get an enol here. Let me just undo that and, well, let me keep it and then we'll show the tautomerization. There's my new bond there. This will tautomerize and you'll get a ketone at the top of your ring. Okay, so those are some pretty advanced cope rearrangement examples. I just want to wrap up today by showing you one other 6-electron reaction. This is called the Claisen rearrangement. This actually came earlier than the cope rearrangement, and you can see it's quite similar in that it starts with a 6-membered chain, 1, 2, 3, 4, 5, and 6. And we have very similar arrow pushing to figure out the products. You form a bond between 1 and 6, 3 and 4 breaks, 5 and 6 rearrange. Your product has a carbonyl already in it. And in this case, we have alkene geometry, which will translate into stereochemistry when there's multiple things to pay attention to. I'm not going to show it in that first example, but you'll see it when we do some of them. It also goes via a chair transition state. This one makes a gamma delta unsaturated carbonyl. I'll write that out. This makes a gamma, remember, use the Greek letters to show how far you are from the carbonyl. Unsaturated carbonyl. Alpha being the one right next to it, beta being one more away, and you just go down the Greek alphabet, gamma and delta. So there's 4 examples of this. Let's see how they work. The first one, I'm going to find my 6-membered chain. 1, 2, 3, 4, 5, and 6. We form a bond between 1 and 6. 3 and 4 break, and in this case the other pi bond rearranges. And if I just draw what happens constitutionally, what does this give me? I have a 6-membered ring down here. Those 2 pi bonds I haven't drawn any arrows for. There's my carbonyl, and then I get what looks like an allyl group hanging off the ring. Now, notice my starting material was aromatic in the end, and this molecule does not like that it lost its aromaticity. So it's going to re-aromatize and undergo a reverse tautomerization by losing that alpha hydrogen. And the reason for that is because it re-aromatizes the ring. Remember, there's something very stable about these things being aromatic, and once it lost it, it immediately regrets it, so it goes back to being aromatic. But we get a completely different molecule. We get a substitution and a new carbon-carbon bond between those 2 carbons. Very clever way of just taking a phenoxy ether, doing a Claisen rearrangement, and getting a substitute benzene out of it. Right next to it, we have a 6-membered chain. I'll number them. 1, 2, 3, 4, 5, and 6. We form a new bond between 1 and 6. We break the bond, 3 and 4. 5 and 6 rearrange. And my product, I'll draw everything the same and just change what's changed. Actually, no stereochemistry here, either in the olefin geometry or anywhere else. You just get a lengthy ketone with a gem dimethyl off on the end. 1, 2, 3, 4, 5, and then 6. Nice example. A couple of other examples just to finish up. C is called an Ireland Claisen. This is not named after the country. This is named after a chemist named Robert Ireland. And there's a sequence of reactions here, and this is a good review of some previous units' chemistry. Remember what LDA does? That takes away a hydrogen to form an enolate. So we have an enolizable hydrogen right there. In fact, I'm going to draw it in. And LDA simply acts as a base to take away that alpha H. You will make an enolate. So this temporarily forms an enolate. And this was a clever way of getting a Claisen precursor, a Claisen starting material. There's your enolate. What does TMS chloride do? Well, TMS chloride acts as a silyl acceptor, silicon electrophile, and you trap the enol ether as a silyl elo ether. TMS stands for trimethyl silyl. So it's SIM3. It's a silicon protecting group. The oxygen-silicon bond is reversibly formed in many organic syntheses. You can form that bond and you can fairly easily break it apart, unlike carbon ethers, which are very stable. Silicon ethers are formable and you can actually reverse them. After that, then step 3, the heat, that's to actually do the Claisen rearrangement. So there's my 6-membered chain right there. I'll just draw the curved arrows. 1, 2, 3 curved arrows. There's my new carbonyl. And then I get what looks like the makings of a carboxylic acid derivative, and indeed that's exactly what it is. You'll hydrolyze this. This is a silyl ester, one could call it. And you'll turn that just into an OH group. This is probably with water, frankly, because you need something that will really hydrolyze this, and you get a carboxylic acid. So quite a sequence of steps that combine some older chemistry with this new Claisen rearrangement. Just to show you we're not limited to making aldehydes and ketones in the products. You can also make acid derivatives, even an acid here. And then one more, just to finish up. This one is the really complicated one because this combines both the Claisen and the cope from the previous, the first half of this lesson. So let's see how this works. This one's a fun one. First, let's find the Claisen, the 6-membered chain with the oxygen in the chain. 1, 2, 3, 4, 5, and 6. I form a bond between 1 and 6, 3 and 4 break, and the pi bond between 5 and 6 rearranges to become a pi bond between 4 and 5. When I draw the product of that, here's what I get. I still have my 6-membered ring. Still have those 2 pi bonds down there. They haven't done anything. There's still a methyl over here along for the ride. I have a new carbonyl right there at the top of the 6-membered ring. I still have this methyl that's on position 1. And now I have 1, 2, 3 carbons attached to that position. 1, 2, 3. There's going to be a pi bond at the end, and then there's also another methyl right there. If you lost track of that, let's fill in our numbers. Where did those 6 atoms go? Well, this is 1, this is 2, this is 3, this is 6, because I form a new bond between 1 and 6, which means this is 4 and this is 5. So this is exactly what we expect. There's the methyl originally on carbon 6, and that's where it ends up. This actually looks a lot like the first one we did, starting with this aromatic starting material. The difference is we can't do a tautomerization, or really a reverse tautomerization, because there's no alpha hydrogens here. But this molecule really wants to go back to becoming aromatic. So that's where the tandem cope comes into play. Tandem meaning it happens right afterward. So I'm actually going to erase those numbers that I just drew on this. That was just to help us keep track of where those carbons came from. And I'm going to renumber it and try to find a 6-membered chain of all carbons to do a cope rearrangement. So I can do that. 1, 2, 3, 4, 5, and 6. And I form a bond between 1 and 6. I break the bond between 3 and 4. That's happened every time. And then 5 and 6 rearrange. What does that give me after the cope? Well, I still have this original 6-membered ring. Always draw the things that don't change first. I still have that carbonyl at the top. I still have this pi bond on the left. I still have that methyl way over there in the upper left. It's been along the ride for the whole time. I now have a new pi bond right there on the right side of the ring between what I just called 4 and 5. And there's a methyl on that carbon number 4. But this bond is gone. I no longer have that. I now have this 4-carbon chain tethered onto what's labeled as carbon 6. So 1, 2, 3, and 4, and it looks like I'm going to have an alkene in that position between those 2 carbons, right in the middle of that tether. I think I would have to track stereochemistry a little bit more going through this, but I'm just going to draw it as a transalkene for now. And we're still not done. This now can undergo a reverse tautomerization. And that's because even though it doesn't have alpha hydrogens here, there is an alpha hydrogen, there's a gamma hydrogen at the very bottom of the ring. Wait, why didn't that happen over here? That's an sp2 carbon. We're not going to break that bond. But this molecule can and will take that H away, and here's how you could draw this reverse tautomerization. It'll break the CH bond, and that pi bond will move up. That's effectively the same or very similar arrow pushing that we see with tautomerization. It's just conjugated. It's separated by an extra pi bond. But when all is said and done, this is what we get. It'd be very hard to predict that. Better question would be, here's what you get. Show the arrow pushing that explains how we get from that starting material to the product. That's a fairer question at this level of the class, but I just decided to show it to you from scratch. Okay, that was a lengthy lesson, but I hope you enjoyed and appreciated some of those complicated reactions that we saw. Most of these I actually learned in a graduate level class back in the day, and it's fun chemistry in my opinion. Okay, thanks for watching.